Hi everybody, welcome back. So in this segment we're going to go over and just quickly do the amplifier alignments for the offset and gain. We're set up for the offset right now. And I'm not even going to get into great details. I'm just going to adjust it. I have the 2 meters connected up to the 2 channels for the offset settings. And we are going to let the amplifier finish warming up. And then we're going to go through and do the adjustment of the DC offset. We're connected to the test points, and we just have to go in, and you can see it's still climbing right now. And we just have to wait for everything to settle and to get up to its normal operating temperature. As soon as it does that, we'll be right back. Okay, the amplifier's been on for about 10 or 15 minutes. These heat sinks are absolutely ice cold. So either the bias is set really low or it's set too low, I don't know, but they're ice cold. We don't have much bias on the amplifier right now. You could just kind of tell. And these have settled in. They're a little bit off 0 volts. I'm on the millivolt scale, so we're going to set this, try to get this as close to 0 volts as possible. I've not replaced the pots in this with multi-turn pots, although I could have done this. I don't think it's necessary. This amp, it seemed to be in pretty good condition, so we're going to adjust this one. And I'm just going to kind of take my time and let it settle. That one looks good. And we're going to go over to this side. See if I can find the pot. There it is. Same thing here. We're going to, the pot's a little bit jumpy. That's kind of hard from this angle. And if it's in that under 5 millivolts range like that, it's good. So this one's right around 1 millivolt and this one's around 1 millivolt. That's perfect. And it'll drift around and it'll go up and down, but as long as it stays, like it is, we're good. So that's all there is to the DC offset. And again, go back and look at all my other videos. I've done tons of them where I've done this and got into a lot more detail how this works. Let's skip ahead now and let's look at the bias. Okay, we're now connected between test points 13 and 23 on the top of the board. And we're looking at the bias, or the idle current adjustment as they call it. We've been waiting a little bit, and they want around 30 millivolts. And of course there's a little typo in here where they're saying, it says, check if the DC voltmeter reads 30 millivolts. If it doesn't read 30 milliamps, adjust to 30 millivolts. So what they're meaning is you are checking 30 millivolts, and it could possibly be that they have the scale set on the design on this amp's design that 1 millivolt equals 1 milliamp of idle current, which would make sense. So you can see these are right on there. I'm not going to touch them. They're dead on. I haven't even had to touch it. This one's 29.9. This one's 28.9. The idle current is fine. I'm not touching it. So we're good. That's all there is to doing the adjustment of the amplifier. I know some of you are disappointed and thinking this would be a big elaborate process, but that's all there is to it. So now we can go on and do some amplifier testing, and that's what I'm really going to focus on for the rest of this video, is some different tests that we can do on the performance of this amplifier. So the first thing we're going to do is have a little bit of fun with the YouTube audio library. I found this song on there called Stranger Danger, and it's on the YouTube audio library, so it's royalty free. And I'm going to play this for you, and then I'm going to stop it, and I'm going to cue into some copyrighted music. I'm just going to play a couple seconds of it just to kind of ask you, I don't know, if you can tell where they got the idea for this song. All right, here we go. cue something in here. Wonder where that song came from, huh? In case you guys didn't know, that's Just Be Good to Me by the SOS Band. Great song, by the way. I love it. But I love some of these songs that I hear on the YouTube audio library, how they don't exactly copy, a cover tune, but get really close, and just kind of hang on the edge there. So anyhow, we were just having a little bit of fun there. Let's get on with some testing. By the way, this amp sounds fantastic. I'm really happy with the way it turned out. Okay, the very first test we're going to do is a very simple one. We're going to apply a 1 kilohertz sine wave tone into the auxiliary inputs of the amplifier. And we're going to use about 500 millivolts RMS of drive signal. And we're going to drive it through just my little Y adapter cable, and I'll show you what this all looks like in a second here. So if you look up there, this orange wire comes out of the signal generator. All right. It goes down into the auxiliary input, and it goes to a split off. You can see the white and the red, and it splits off through a couple of resistors. I believe they're 470 ohm or 1K. I think they're 470s. And just splits off into the two inputs. Now, we're coming out of the speaker terminals of the amplifier, and we're going into the resistive dummy load. And this is just a board that I made that allows me to switch between 4 ohm and 8 ohm dummy load. It also allows me to switch between times 10 and times 1, and it's a very accurate divider, so that I can actually have a 10-to-1 ratio on the output. That means if I have 10 volts being applied to the speaker terminals, I get 1 volt out to the oscilloscope, if that makes sense. And it's very accurately adjusted, you can see, with a pot and a precision resistor. Now this connects to 4 big 4 ohm 1000 watt non-inductive resistors that are on the rear of the bench. I'll flash up a picture of them. When they're in series, it's an 8 ohm load per channel, and when they're by themselves, they're 4 ohm load, and I could technically put them in parallel to make a 2 ohm load if necessary, but I usually don't do that. But it can be done. Moving over to here, I have the oscilloscope set up, and this one actually I wrote a little math expression and saved it as a setting. So if you notice, I have both channel A and B turned on, and of course channel A is the left channel, channel B is the right channel. So left channel is yellow and the right channel is blue, and you should be able to see that right here. There's the yellow and the blue, see that? And we just put them on top of one another. And the red trace right here, you see, is the math expression. And what it is actually doing, it is taking the RMS value of the voltage of the signal that's on the left channel, because it only measures the left channel, one channel at a time. And it does the Ohm's law formula for an 8 ohm load. I also have a program in here for a 4 ohm load. So what it'll do is it'll directly read the wattage at the same time that I'm seeing the waveform and the amplitude of the waveform. So it's doing that, and it will monitor the frequency of that sine wave. So with that little program setting, we can monitor a whole bunch of things all at the same time using just a 1 kilohertz tone into an amplifier. So now that you know what we have, let me start turning up the volume, and we're going to drive the volume up until we see the amp clip. And there's some things we're going to find out from watching the amplifier clip, okay? So the first thing, as we go up, you can see it starts climbing in amplitude. Each click, you can see, is one click of the attenuator volume control. And as I go up, you can see both of the waveforms are pretty much staying on top of one another. And you can see where we are right now. We have about 99 watts into that channel. So this is an 80 watt amplifier, if you remember. I'm getting a very clean 99 watts. And if I go up a little bit more, you can see it starts to clip. You see how it gets flat on the top and the bottom? That's actually a good thing. What you want is, if it clips properly, you should see both the top half and the bottom half of the waveform clip exactly at the same amount at the same time. Remember, this amplifier has a split power supply. It has a positive power supply and a negative power supply with reference to ground. And it's called a push-pull amplifier, meaning one set of output transistors, or one output transistor in this case, handles the positive going half waveform, anything that's above 0 volts, and the other transistor handles the negative going half of the waveform, or the negative voltage with respect to ground. Okay? And if they're both set properly and they're both doing their jobs correctly, each one should kind of hit that maximum voltage of the power supply at the same time. And what we just saw there when we were looking at that clipping is that's exactly what's happening. Now, let's say one side started to clip off before the other. We refer to that as asymmetrical clipping. And that would indicate that there's something wrong with the drive signal or something like that in the amplifier, and we would want to look into why that is happening. Okay, so there you go. The first test tells us a lot. So we can see, number one, if that sine wave does look like a nice looking clean sine wave. We can look and see if we have symmetrical or asymmetrical clipping, and we can measure the amplitude or the maximum output. We can measure the wattage, and we can even look at the frequency. So you can see our 1 kilohertz frequency is showing up as 1 kilohertz. And if the two waveforms fall on top of one another, here's channel 2, channel 1, you can see they're perfectly tracking. If they weren't, then we know we have a problem either with the volume pot, with the balance control, or something worse, maybe the two sides of the amplifier, right and left channel, don't have the same gain or something. But as it is on this one, you can see it's perfect. It's tracking perfectly. So this is all good news, and this is a really quick preliminary test you can do to see if your amplifier is working properly. So we were running this amp pretty hard just now, right? So let's look at the heatsink, and I can feel it's just barely lukewarm. And if we check the temperature, you can see it's only 97 degrees. So it's right around body temperature for us, huh? So it's not that hot. And that's a good sign. That means that the amplifier is running cool. It has adequate ventilation and heatsink, and there doesn't seem to be any heavy DC or anything like that. So again, amplifier is working well. Okay, another note for those of you who may want to service one of these receivers. I have the power supply board here on the camera, and you can see there's 3 transistors here, and I've actually changed them out. Here's the original heatsink and transistors. There were 2 NPNs and 1 PNP. This is the PNP. It's a 2SB682, and then the other 2 are 2SD712s. And you can see the tiny little heat sinks that are mounted to these. Compared to the new ones I put in, they're very small. And these things run blistering hot. Now, I did a few calculations, and for each one of these, just sitting at idle, these are dissipating about 1.5 to 2 watts of energy. Now, I don't have a chart for the transistors, how many watts of dissipation equals how many degrees temperature. A lot of that is very dependent upon the air circulation, the heat sink you're using, and all that. But what I do have is I replace these transistors with new ones, because when they run at high temperature like that for long periods of time as they age, they actually will start to, the gain will start to deplete on them. They will get tired out. So I will replace these ones that run hot. All this Pioneer gear from this era, with the linear power supplies like this is an issue. Okay, so I've done a whole bunch of, even the big ones like the SX 1050, 1250, 1280, the 1980. These transistors get really, really hot. So because of the concern for that, I wanted to look at if this thing is operating in its safe operating range, which I believe that it is, even though this is really hot. When these get to their maximum temperature, I'm measuring somewhere around 60 to 70 degrees Celsius on each one of these heat sinks, and they're all tracking at about the same temperature, which makes sense because they're all dissipating right around that 1.5 to 2 watts. What I mean by dissipating, that's the amount of energy that is used up and converted into heat within the transistor. Because these are semiconductors, right? They turn on, and they will, some of the energy will be dissipated as heat, and some of it will be passed through. And don't need to get into transistor theory here, but I ended up replacing these with KSC 2073s and KSA 940, and those are the complementary pair that I used, and they're well within the ratings of what these are. 25 watt transistors, so they're not even breathing heavy. But when they run really hot like that, there's a derating chart. So here's the chart for the KSC 2073, for instance. And the very last chart here is the power derating chart, okay? And if you look, what they have is they show the case temperature of the transistor down here versus the wattage that the transistor has to dissipate. And you can see it's the opposite of what you would think. The more power that you need to dissipate, the cooler you have to keep the transistor so it doesn't go into thermal runaway. So to get the full 25 watts out of this, we have to keep the case temperature down below 25 degrees Celsius. So that's why you would have to put a great big massive heat sink on there. But if we look around the 2 watts of dissipation, which here this is 5 watts, so 2.5 would be about halfway here, right here. You can see this thing can run clear up between 125 and 150 degrees Celsius, so somewhere around 130 to 135 degrees C this can run. We're running somewhere around 60 to 70. So let's say 75, just for safe margin. We can actually dissipate about 15 watts before this transistor will start to be damaged from the heat. So we're well within the tolerance, even though when you touch these, they're really hot. You can't keep your hand on them. Like I just turned this amp on before I turned the camera on. And if we look at this, I'm already up to 64 degrees C. And on this other one, 67. Where am I at here? There, 66. And this one over here is 63. And it'll keep going up. I mean, if we keep monitoring this as it stays on and idles, you see it just goes up and up. So the good news is it is well within its range. I put these slightly larger heat sinks on here. And this one on the right, I actually had to put an insulator and a mica pad because the collector of the transistor is connected to the little mounting tab. So if these were both directly connected to these aluminum heat sinks and they touched one another, you would be shorting the two collectors together. So what we did was by putting this one up on an isolation pad and putting a little insulating ring on there, if that happens, there's no danger in the transistors shorting each other out. Just something to be aware of when you do all this. These larger heat sinks have made a difference. These little ones were running even hotter because they couldn't dissipate the heat as quickly as this one that has the fins and everything. So just another little tip there for you. Okay, next we are going to look at what the distortion figures look like on this amplifier at 1 kilohertz. And you can see we did this already. We're going to drive this up. We're going to take it right below the clipping, right about there. And let's see what that is. That's 112 watts, okay? And I'm going to move this over here. And you can see idling at 112 watts, we're at 0.6 distortion, 0.06 some. And if I drop it down just one notch, drop it down to about 60 watts and see it drops way down. And drop it down to a reasonable 55 watts per channel. It drops even more. And down around 35 watts per channel. And we can see it's getting very, very low now. Down to the point where the the meter is actually starting to, you're seeing some of its internal distortion. So now let's move over to the right channel and hopefully get the same results. We'll see. Let's move this over. And once again, we'll go up to our 100 watts per channel. And there it is, just about the same. Drop it down. Back down to our, that's 90 or about 57 watts per channel. Just about 60. Down another notch. And we're back down to our 36 watts per channel, 35, whatever. And drop it down a little more. And we can see it's very minimal now at 22, 23 watts per channel. So the amp, at least with a simple sine wave, has very good distortion characteristics for both channels. No difference. And both channels match very well. Okay, for our next test, if I have this hooked up right, we're going to do frequency analysis. And we're going to look at the left channel first. And we're going to look at the frequency, which is gain versus your phase relationship of input versus output. Now, the gain is really not going to be very important what level the gain is, but what's most important for us is we want to make sure that it passes an equal amplitude of signal in a flat manner. In other words, all of the frequencies from 20 hertz up to 20 kilohertz are going to be swept through this amplifier and measured. They're all going to be at a consistent amplitude. So with that in mind, if the amplifier is amplifying the signal without coloring it in any way, it should have a flat gain curve. In other words, however much gain there is from the input of the amp to the output of the amp, that should be the amount of, it should be the same all the way across the board from 20 hertz to 20 kilohertz. Now you have to take into consideration these gain values in dB are not going to be super accurate. Well, the dB isn't going to matter because I'm on my dummy load, I actually have a 10-to-1 reduction. So in other words, for every 1 volt RMS of output from the power amplifier into the speaker load, the dummy load, I'm actually only going to get a representative voltage of 0.1 volts. So in other words, 0.1 volts equals 10 volts. So our curve is actually, you'd have to multiply it by 10 if you wanted to get the actual gain of the amplifier. Does that make sense, or am I confusing the crap out of you? I just confused the crap out of myself. Anyway, let's do the test. Now, another thing I'm going to tell you is we're going to do this at very low volumes. I don't want to do it at high power right now. We're going to do a low power test first, because we want to see how this amp works at very low listening levels. Because remember, that's where you're going to have the most influence of things like your bias, your DC offset, any reactive influences of some of the components in the audio path. Those things are really going to show up at low volume, where we tend to listen to things a lot of times, you know. So I am driving 100 milliwatts roughly into the dummy load, and we're going to do the test. Okay, here we go. Flat as a pancake. How about that? And it just starts to tailing off a little bit at 20 kilohertz and a wee little bit at 20 hertz. And actually, that's kind of the range of this mixed domain oscilloscope for this particular test. So part of that could be the test equipment. You can see we do have a little phase change, and let's scale the plot. Again, this is the software. No, you can't turn this off. It automatically scales everything, whether you want it to or not, instead of leaving it at 0. So setting everything so we can compare. So there's our first plot, and this is for the left channel. Now we're going to do the right channel and do the same thing and compare them then. Okay, I've switched over to the right channel, and let's see what it does. Okay, so now let's go and scale it once again to get everything zeroed. The reason I do this is I want them both to be scaled exactly the same way, so you can compare apples and apples when you're looking at channel 1 versus channel 2, or the left versus the right channel. Because these will adjust to make everything kind of be in the middle of the screen, which we don't care about. So there you go. And that looks, to me, looks pretty similar to our other channel. So now what I'm going to do is I'm going to take a snapshot of both of these, and we're going to put them up on the screen now and compare them to see how close they are between right and left channel. All right, now we're going to do another test. And you can see I have a piece of paper here, and I have the word slew rate written down. So what is slew rate? Well, slew rate is the rate at which the amplifier can make a rapid change from one voltage level to another. Now, why would you think that's important? Well, the higher the frequency that you want to reproduce sound-wise, the faster the rise time of that signal has to be. In other words, 20 kilohertz, that means that thing has to be able to go from 0 volts up to its peak and then back down 20,000 times per second, right? And actually, for one cycle, it has to do that twice, because it has to go up to the positive swing, then cross the 0 crossing and do the negative swing. And it has to do that complete cycle 20,000 times every second. Now, if you want to reproduce a waveform accurately, clear up to an extreme one, which would be a square wave, that has to be able to do that. If there's any delay in the change of the voltage, let's say there's some sort of a reactive component in the amplifier or something, what's going to happen is it is going to distort that waveform at high frequencies. Now we can actually calculate what kind of slew rate we need in order to reproduce the audible frequency spectrum. So it is generally accepted that the highest frequency that the human ear can hear on average, I know some of you have super ears and I have crappy ears, but on average is about 20 kilohertz. That's the generally accepted norm. And to be able to reproduce 20 kilohertz accurately, you need to have a certain slew rate. And there's a way we can calculate it, and that formula goes slew rate is going to be equal to 2 times pi. That's a terrible looking pie, isn't it? That's why my wife makes all the pies in the house. I'm good at eating pie. I'm not good at making pie. Times the frequency. All right. And the frequency is the desired frequency times the maximum voltage or the peak voltage that it has to reproduce. So obviously, the higher the power of the amplifier, the faster the slew rate has to be, because it has to be able to go from 0 volts to its maximum rail voltage in that amount of time. So slew rate is actually dependent upon 2 things, upon the frequency that we're interested in reproducing and the amplitude of that waveform. What you're going to find out is somewhere in that 100-watt amplifier range, you're going to have somewhere around 7 to 8 volts per microsecond rise time. How do we figure that out? Well, let's say our slew rate equals 2 pi, and we want 20 kilohertz, right? So that's going to be times 20,000. And then for our V, for our voltage, right, we got to do a little bit of math. So for a 100-watt amplifier, we first have to find out the peak voltage that we need. And we're going to use a little bit of math for that. So first of all, we have to figure out the RMS voltage. And we need to know the load. So let's say it's going to be an 8 ohm load. Okay. So your voltage RMS is going to be equal to the square root of your 8 ohm dummy load times the wattage that you want. Okay. P for power. So that's going to be equal to the square root of 8 ohms times 100 watts, which is going to be the square root of 800, which is going to be equal to, which is going to come out to be about 28.3 watt, 28.3 volts. So let's just say around 28 volts or so. Now that's volts RMS. And if we want to know the peak of that, the peak is going to be 1.414 of that. So we're going to take V peak is going to be equal to 1.414 times the 28.3. And if we do that, 1.414 times 28.3, you need about 40 volts. Okay, 40 volts peak. All right, now that we know the voltage for a 100-watt power into a 8 ohm load, we can plug that up to here, which is 40 volts, right? So now all we got to do is 2 times pi, right? Pi is 3.14, so we're just going to round it to 3.14. So 2 times pi would be 6.28. 6.28 times 20,000 equals times 40 is a big old number. And now this is going to be, remember, we have to divide this over by microseconds. So we have to move this over 6 decimal points. So 1, 2, 3, 4, 5, 6. So you need about 5.02 volts per microsecond. Does that make sense? Or that many volts per second. That's giving you the volts per second, because the time is at frequency is in seconds, cycles per second. Everything we have to convert the units. So that would be 5 volts per microsecond. Okay. So now we know if we have a 100 watt amp, this is an 80 watt amp. Okay. We know that we want to have something somewhere in the line of 5 volts per microsecond for this to be safe. Okay, or just a little bit below that, since it's technically an 80 watt amp, but if you notice, we were getting 112 watts out of this thing. How are we going to test that now? Okay, we're looking at the oscilloscope now. I'm just going to start a waveform, and I'm going to get it up until I get somewhere around that 40 volts peak, or just below. Actually, we want about 35 volts or 36 volts, something like that, to get near that 80 watts. And once I do that, I'm actually going to freeze or just stop the sweep to store the image. And then we're going to go and we're going to take some measurements. Okay, here we go. I'm going to drive this up, and then I'm going to freeze the waveform so I can turn the volume down. You don't want to run the amp very long, and you have to make sure that the amp can handle a square wave. That's very hard on an amplifier. So we see right there's about 75 volts, okay? Peak to peak. What? So we calculated for volts peak. That would be from the 0 point to the positive going, or the 0 point to the negative going. But what we're looking at here is peak to peak. See, from here to here. So if you need 40 volts peak, then the entire waveform would have to be double that, which is 80 volts peak to peak. Okay, so if you see, this doesn't look very square, does it? It kind of looks rounded. And this is what's called the rising edge. There's also a falling edge, where the amplitude is going from the positive down to the negative power supply. So this middle point would be idle, would be no sound. Okay, this is a push-pull amplifier in action. So the positive power supply and the NPN transistors in this case would handle from here up to here, and the negative power supply, which is the negative, 50 volt supply or whatever, going from negative voltage positive to the zero crossing, and the PNP transistors are handling that half of it. So really what you're seeing here is you're seeing the PNP transistor side turned all the way on, and then it's slowly turning off, and then the NPN or positive voltage side turns on and takes over, and it increases the amplitude all the way up to the peak. And that's how it works. So now if you have a little bit lower end oscilloscope, your digital one that is, you can use the cursors. Where are they at? Turn on the cursors, and you can actually adjust, measure it, your amplitude, and then you could measure your rise time. But we're not going to do that, because this scope actually has a little bit nicer feature where you can actually directly measure it with the measurement function. So if I back you out, you can see I already put that up there. And you can see the rise time for this is about 9.7 microseconds. So to go from here to here was about 9.7 microseconds. And the peak voltage, if you see there, we have peak to peak is 7.52 volts. See that? So from here up to here was 75.2 volts. Remember, we're using our 10-to-1 divider. I bet I'm confusing you guys with all this stuff. You got to keep this all straight in your mind, right? So we basically went approximately 75 volts in 9.7 microseconds. So let's do the math. Okay, 75 volts divided by 9.7 microseconds, right, is about 7.7 volts per microsecond. And what did it say we needed for a 100 watt amp? It said we needed somewhere around 5.02 volts per microsecond. So this exceeds that, which means we should be able to reproduce a 20 kilohertz sine wave at full volume and just get minimal distortion. Now this is bare minimum. If you want to reproduce a perfect square wave, you're not going to do it. As you saw, there is a rise time and it was distorted, right? So the faster the frequency gets, the more distorted it's going to get. So what that means is, by looking at this, I'm guessing that if we're at 20 kilohertz, you're going to get a really wonky looking square wave. Let's see if I'm right. Okay, I changed the volts per division to 1 volt per division, or 10 volts per division. We're not going to run this at super high power because I don't want to run this thing at max power at 20 kilohertz square wave. It's not good for the amp. But let's see what our square wave looks like at 20 kilohertz. And you can just monitor it as we go along by looking down here where it says frequency. This will tell you the frequency. Okay? So you can see it's singing 20 kilohertz, but that doesn't look very square, does it? Kind of looks like a sawtooth almost. Now what do you think will happen if we go back to a sine wave? Okay, I'm now going to switch to a 20 kilohertz sine wave. Let's see what that looks like. Not bad, huh? Not too bad at all. So you can see that it can reproduce a sine wave at that frequency. And it probably can even go higher than that, because if you remember, the bare minimum we needed was about 5 volts per microsecond, and we had somewhere around 7, right, is what we were getting. So let's go up to 20 kilohertz and see what it does. Or 30 kilohertz, I'm sorry. 30 kilohertz. Okay, here we go. And you can see it still looks pretty good. And you can see it starts to get a little bit, but some of this, that's pretty good. 30 kilohertz. All right. And even 40 kilohertz, it's still there. 50. And you can see the amplitude goes way down, but there's 50 kilohertz, 60, 70, 80, 90, 100 kilohertz. Not bad. So as far as a sine wave is concerned, that slew rate is just fine. However, the less of a sine wave it is and the more of a square type wave it is, the more it's going to be distorted after you get past a certain point. Hope that makes sense. Again, these are just interesting things. These aren't things you normally would do with your amplifier when you're testing it. These are just some interesting things that you can test if you want to learn more about how all this stuff works. All right, after all of that, it is time for the village idiot to speak. We've done quite a few tests on this video. There's a few more that we could do. There's actually a whole bunch we could do, including, for instance, we can do a two-tone intermodulation distortion test, and we can use the 3580A spectrum analyzer. If you guys are interested in that, maybe we can do it on another video or something. But I think what we've done on this shows that the amplifier is performing very well. And I think we can move on to do just the tests and alignments if necessary, which I highly doubt, on the tuner section. So I'll go over some of that in another video probably. But one thing I wanted to share with all of you, I got a lot of great comments from the last video, and some of them were concerning the input capacitor that we talked about. Remember when we were using, let's see if it's still even here, they were originally using 2 capacitors with the negatives tied together to make it like a non-polar electrolytic capacitor. And we were talking about how the ESR doubles with this. And a lot of you said correctly that that couple of ohms of ESR doesn't mean a hill of beans. And it doesn't. These are low noise capacitors. They don't really worry so much about the ESR on these. And that's not the purpose. But the point that I was making is that there are different capacitors, and I'm still curious, and I've not had my question answered yet, at least to my satisfaction, where I can buy into it, why they did this. First of all, I don't see a need to have a non-polarized capacitor in that position. Every other amp that Pioneer made in the, similar to this one, they all use just a regular low noise, one of these orange polarized capacitors on 1 microfarad. The biggest explanation I got, or the most valid one, was they did this because it's cheaper than putting in a film capacitor, and it's still a little bit smaller. Well, if it's cheaper to do this, it would even be cheaper yet to just use a single 1 microfarad orange capacitor. So I still don't understand the purpose for doing this, and nor do I understand the purpose why it needs to be non-polarized, or if it does need to be non-polarized. I don't know. But one thing I will share with you, throughout this entire video, we have actually been doing some other tests in the background. Because if you look over here, I don't know if I can get the camera far enough down in. Right there you can see we have the, I don't even know if you can see it from here. It's right down there, see it? We have those original, like I said, the KL series, which are good replacements for this. However, on this side, I removed those and I replaced it with a single film capacitor, like what we tested. It's a 1 microfarad. So throughout all those tests that we did, we were actually experimenting to see if there would be any difference at all between using the film capacitor or using those electrolytics. And as you could see, there was absolutely no difference. I'm sure that if there was something in there, it would have shown up in our tests, because we did quite a few of them, didn't we? And as you can see, it didn't make a hill of beans worth of difference. We now know, don't we? And most of you were right. So just goes to show we share information and we learn. And that's what I like about this channel. That's what I like about doing what I'm doing. That's what keeps me doing these videos. I mean, you know, it's a lot of work for me to sit here and film all this stuff and share it out there with all of you. But the feedback that I get from you helps me to learn too. And if you read the comments, we learn from one another through the comments. So I think it's a good thing for all of us, and that's why I keep doing it. But anyway, this was an interesting video to make. It was a lot of fun. And next one will be the tuner, and then we're going to get this thing off the bench, and who knows what will go on to the next thing. I want to thank you all for your comments. I want to thank you all for all of the well wishes and everything. And again, I wish you all peace, joy, happiness, and good health in your lives. And we'll be back real soon. Until then, take care. Bye-bye.